Let us discuss reactions in aqueous solutions. This is chapter 4. You're looking at brightly colored solutions. There could be a reason for that, which is reactions in there that are creating the emission or causing the emission of all those different colors. But let's discuss on this. What are our learning objectives? The general properties of aqueous solutions. Remember, you know you have an aqueous solution if you have dissolved ions. That's what determines an aqueous solution. For example, you put sodium chloride in water, it gives you NaCl AQ. AQ stands for aqueous. All right, we'll discuss that. Precipitation reactions, these are reactions which are accompanied by solids formation. Reactions that form solids in solution, and then acid-base reactions. These are neutralization reactions, for example, sodium hydroxide and HCl. And titration, by the way, is an acid-base reaction most of the time. And then oxidation reduction reaction, this is where we're going to discuss redox reactions, asking ourselves who lost electrons, who gained electrons. Concentration of solutions will determine concentration of solutions in terms of moles per volume, which is a liter. What we call uppercase M, what we call molarity. And then gravimetric analysis is where you're doing a reaction and you can actually get the mass of your product. And of course, titration, which happens mostly to be acid-base reaction that determines the concentration of an unknown solution using the concentration of known solution, otherwise called the standard. Okay, solutions. What is a solution? A solution is made when you take a solute and put it in a solvent. Chapter 1, we talked about this and we said that there are different types of solutes. Solutes actually are substances present in small amounts in the mixture, so to speak. So a solid can be a solute like sodium chloride, a liquid that is in less amount in a mixture with another liquid will be a solute. Gases can also be solutes when you're dissolving a gas, a little sample of gas in a liquid. Also, solvents can also be liquids or gases, or even solids, as we will see in the table on this slide. Going back to definition of a solution, that's a homogeneous, meaning same type composition, homogeneous mixture of two or more substances. For example, sodium chloride salt solution. The solute, like I said, is or are substances present in smaller amounts. Okay, and then the solvent is a substance present in the larger amount. Looking at this table, you will say that soft drink is a solution, because it's made of water plus sugar and CO2. Air is a solution. I told you solvents can be gases or liquids. Air is a solution because it's composed of nitrogen gas in large amount, and then oxygen, argon, methane will be in less amount. Soft solder in solid state, looks like even solids can be termed as solution. And you see lead here is the solvent because it will be in the greater amount in salt solder. So anything in greater amount in the mixture is going to be taken as a solvent. And then this is tin in lesser amount in the mixture. Here you're looking at aqueous solutions of potassium permanganate. One is deeply colored, the other one is lightly colored. So this is deep color, this is light color. So the difference here is what we call concentration. The amount of potassium permanganate KMnO4 in a given volume. Concentration is different. So the one with deep purple has a lot of potassium permanganate. The one that is light pink, that one has less amount of potassium permanganate. We say it's dilute, while the other one here is concentrated. Let us learn about electrolytes. The learning objective here is to be able to identify strong electrolyte, non-electrolytes, and weak electrolytes. An electrolyte is a substance that, when dissolved in water, results in a solution that can conduct electricity. And the reason is electrolytes will have free, so let me write this, they have free moving ions. For example, Na plus, Cl minus. These ones usually exchange electrons, and because those electron exchange are involved in ionic compounds, then you expect that good electrolytes will conduct electricity. So the more ions you have, the better. On the other hand, an electrolyte is a substance that, when dissolved, results in a solution that does not conduct electricity. In other words, this one lacks free moving electrons, or you can say the molecule does not ionize at all. For weak electrolytes, you have partial, you can even say few ions present. In that case, it's gonna glow dim. This is the non-electrolyte, no glow. Why? The reason is no ions in solution. The weak electrolyte, there is partial ionization of the molecule. For example, ammonia does not break down easily in water. Gives you a weak electrolyte. Oh, let me give you another one. The active molecule in vinegar, ethanoic acid or acetic acid, it partially ionizes. It's a weak acid. So you can say that weak bases, weak acids. Ammonia is a weak base. Acetic acid is a weak acid. So weak bases, weak acids will generally give you weak electrolytes. You can also safely conclude that strong acids and bases will fully ionize in water to give you a lot of ions, like sodium chloride will give you a lot of ions, but that one is neutral. But I'm just saying, if you have strong acids or strong bases, they're automatically going to give you strong electrolytes. But you have those other salts that are neutral, like sodium chloride, KCl, KNO3. Those are still strong electrolytes because they fully ionize. Strong acids and strong bases usually fully ionize. And so those ones, alongside the neutral compounds like sodium chloride that fully ionize in solution to give you lots of ions and electrons, they will make the bulb glow so bright. So this is the brightest. So the solution in there is a strong electrolyte. So characteristics of electrolytes, that's what I've already said. Number one, they're going to conduct electricity in solution. And number two, they break 100% in water to form 100% ions. For example, solid sodium chloride will give you maximum Na plus, maximum Cl minus. If you're looking at potassium nitrate in H2O, it's gonna give you maximum K plus and maximum nitrate. Okay. However, if you're looking at the weak electrolyte, they do not completely dissociate. So the word I use is partial. So they partially break down in water, partially dissociate in water to give very few ions. So example I gave you is your acetic acid or ethanoic acid. This one barely gives you a lot of ions. So in fact, what we use is equilibrium arrows, where to form the ions is unlikely. This reaction will go back. The back arrow is longer than the forward arrow. So these are very few ions. If there are very few ions, you have low conductivity, we say that's a weak electrolyte. Okay. Like I said, you use equilibrium arrows because of partial ionization. It's reversible. Therefore, that means that if the reaction is reversible, you're going to have very few ions formed. Very few ions formed in solution. And therefore, ethanoic acid is really a weak electrolyte. Okay, it's a weak electrolyte. Acetic acid is a weak electrolyte because its ionization does not go to completion. It's incomplete. It's partially ionized in water. The other one I gave you an example was ammonia. You put ammonia in water, he will partially ionize to give you ammonium. Okay, to give you ammonium, NH4, not NH3 plus. That's a cation, and then the anion is hydroxide. So again, these will be very few, which is why I told you weak acid or weak base. These are weak base. Weak acid or weak bases, they are always forming solutions that are weak electrolytes. Okay. Ethanoic acid is a weak electrolyte because it's a weak acid. It's a weak acid because it partially ionizes in water to give you few H pluses, protons. That's about electrolytes. But you know the application of electrolytes. I hope you know that if you go to the hospital and you're low with electrolytes, your blood is low in electrolytes, they'll force you to start drinking electrolyte-based fluids like Gatorade, Sprite, I believe, many others, just to balance it's called ionic balance. Otherwise, your nerves will be struggling, headaches, so many things will go wrong, your kidney function, nerve function, so many things will go wrong. Hydration, as the word goes, this just means to add water. If you say you are dehydrated, it means you've lost water. However, in chemistry, we would say hydration is addition of water around an ion. So by definition, officially, hydration is the process in which an ion is surrounded by H2O molecules arranged in a specific manner. Okay, so I want you to focus on the structure of H2O. We know it's bent molecular geometry. We know it's polar because of dipole moments pointing towards the oxygen. The oxygen is partially negative. The hydrogens are partially positive. We know that. So if you are to attract a positive charge, which is what's shown in purple in here, the oxygen must be very, very near the positive charge. So which is why you see the red balls close to the positive charge. The red balls are the oxygens. That's that. On the other hand, let's talk about a negative charge. We've said that oxygen is partially negative, hydrogen is partially positive because dipole moments point toward the electronegative oxygen. So same thing will happen here. That makes water have a net dipole. We talked about this in a previous chapter. Water is polar. So if oxygen is partially negative, the hydrogens will be partially positive, correct? And therefore you expect that partial positively charged hydrogen is going to be attracted to a negative charge, which is an anion in solution. So the anion will be attracted to the H+, but the cation is going to be attracted to the O- of water. Remember, like I said, oxygen is partially negative because of dipole moments pointing towards the oxygen, which is why it's saying that hydration is a process in which an ion is surrounded by water molecule arranged in a specific manner. So if it's cations, the water has to face the cation, because oxygen partially negative, cations positive, opposite charges attract. If it's an ion, then the hydrogen has to face the anion. Hydrogen is partially positive in water, the anion is negative. So that's what this diagram is showing. Specifically, this happens in electrolytes, where the cation, like Na+, is separated from an ion like Cl- by help of hydration process, where you see the water molecules surrounding the cation like sodium plus when you dissolve table salt in water. Here, the anion is trapped by partially positive hydrogen of the water. So what happens is that now the cation Na+ and the anion Cl- are completely separated in the water, in the bulk of the water. The water is a solvent, sodium chloride will be the solute. You have this freely moving cation and anion, then you have a strong electrolyte in the process of dissolving sodium chloride table salt in water. Continuing with electrolytes, you'll notice that non-electrolytes do not conduct electricity. And the reason is simple why they do not conduct electricity is because they do not form ions, they do not ionize, they do not form ions in water. The best example is glucose, which is a sugar that will not ionize. You see it here. Beer, okay, methanol, urea, sucrose, these sugars, they usually stay intact as a unit molecule. They don't break apart. These formulas don't break apart compared to HCl. HCl will break apart in water to give you H+ and Cl-. Nitric acid will break apart to give you H+ and nitrate. Okay. This one will also break apart to give you all these ions. This one gives you this one will firstly give you one hydrogen, one proton plus HSO4-, which becomes a weak, this one becomes a weak electrophile. He has a negative charge. Sodium hydroxide, strong base, breaks apart maximally. Barium breaks apart maximally to give you those ions. These are strong electrolytes, and other ionic compounds that are not strong bases or acids, the neutral compounds like sodium chloride, potassium nitrate. For weak electrolytes, I talked about the active ingredient in vinegar, ethanoic acid, partially ionizes, and we talked about that. Okay, it partially ionizes, so we used an equilibrium. Where's the equation? Here it is. We use an equilibrium arrow because it's a weak acid. It gives you very few ions in solution. Same thing with ammonia, is a weak base. It gives you very few ions of ammonium ion and hydroxide ions in solution in water. Okay, so which is why ammonia is right there. These are weak acids. That's a weak acid. Okay. Water is also a weak electrolyte. It barely ionizes in itself. So highlight non-electrolytes, they do not ionize at all. They stay intact as a unit molecule, and that's what you're seeing in this equation right here. Your glucose in water does not form ions. It stays intact as a molecule. No ions formed. No ions formed, no electrical conductivity. Okay, so that's why non-electrolytes do not conduct electricity, because there's no ions, there's no cation, there's no anion formed.